we go. All right. Good morning, everybody. How's everybody doing this morning? Hopefully you're doing okay. It's a nice, bright, sunny morning in May. The birds are singing. The plants are growing. The lawn needs mowing once again. So, I just wanted to, by way of announcements, I just wanted to go over one thing with you guys before we get into the lecture material today. Apparently, a reasonably large number of people in the class have been submitting their assignment files with the wrong name format. So let me explain a little bit why it's important that the naming convention occurs the way that it does. So, a lot of people have been inserting things like their name or their MAC ID into the file name for their assignments, and we would like it if you didn't. We would like it if you just kept the file name the same as the, as received by you from either Avenue or Jupiter. Just leave the file name alone. The reason for that is we don't require any special designation within the file name to be able to tell whose assignment is whose, because that information is conveyed by the directory structure that exists on the Jupiter server. Even the stuff that's submitted through Avenue is migrated by us to the Jupiter server in a reasonably automated fashion. So you don't have to include that stuff. We aren't going to not know whose assignment it is, because that's all taken care of by either which account it was submitted from on Avenue or which folder it ends up in on Jupiter. And in fact, it's if you have renamed the file, we run into a similar issue with the software that we use to run the to grade the assignments. We run into a similar issue if the file has been misnamed, as if a function is misnamed inside of the assignment. Specifically, the software can't find it if it doesn't have the correct name. And if it can't find it, then you get a 0. Now, this is the first assignment, so a certain amount of mercy will be extended to all of the good citizens of this planet with respect to having named things the wrong thing, at least with respect to file names. It depends on how... mileage may vary. I'm not guaranteeing that in all cases we will extend mercy for naming such things. But please understand that the amount of forgiveness that we have for not following these conventions will be dropping off precipitously after the first round of submissions, which were due 3 minutes ago. So on the next assignment, we expect you to be adhering to all of the naming conventions that are specified in the instructions for the assignment, because it is not sufficient for you to merely be able to program. You also have to be able to follow instructions. That's a perfectly fair thing to grade people on, is their ability to follow instructions. So, that is all true. Use function names exactly as specified in the question. That applies to classes and attributes of classes as well once we get into them. And also, do not change the names of files, assignment files, as received from the server. Just don't do it. So there you go. Hopefully that's sufficiently clear for everybody. Yes. Yeah, as David points out, the names... Oh. No, David. It should be a1.ipynb, not .py. We're not accepting Python source files either. They have to be Jupyter Notebook files, not Python source files. That's the other thing. So yeah, that's also a very important thing to note. We're not like a similar level, like this time we will accept if you formulated your answers in the form of a Python source file, we will accept it this time, but not for any assignments going forward. If you want the grades, you're going to have to put it in a Jupyter Notebook from this point on. Right? Okay. Gotcha. Good. There we go. No trouble, David. No trouble. Just, want to make sure that the information is accurate. Very important, accuracy. So, let's see, where were we? We were talking about structured data types. Nope, that's... structured data types. All right, so actually I think we had just finished it. Yeah, now that I remember, we actually finished the we finished topic 4. Excellent. All right. Give me 1 second, folks. There we go. So up to this point, we have been covering primarily the type of material that you're likely to have seen if you had gone through a book on elementary programming. If you'd gotten maybe, a third to halfway through a, like programming for dummies type book or something like that, right? Maybe not that much. We're a few chapters in at any rate. So what we're going to talk about in this topic is the type of stuff that that's less likely that you would find in an introductory programming manual. We're going to be talking about functions and recursion. Recursion is sort of the, shall we say, the take-home concept from this set of lecture slides. It's a more mathematically abstract way of conceptualizing data processing. It takes a little bit of effort to wrap your head around it mentally. We're going to go through it, at a reasonable clip. Hypothetically, we'll get this topic done within the next 3 hours. But, yeah. I'm not sure I have much to say. Functions you should already know about, to some degree at least. We're going to show you some cool little tricks that you can do with functions, though. So, functions. We've been using functions so far. Functions are a way of abstracting. They're an abstraction mechanism. So, if you have a series of instructions, in a computer program that you think, A, you may repeat frequently, B, you may want to enter into the same block of code with different preconditions, i.e. with different values of different variables, or maybe it's just that this set of instructions, they function as one cognitive unit, right? This is one operation, right? In these types of situations, it's common to package up instructions as functions. Functions are primarily a mechanism for bundling up a set of instructions and giving them a name. So, a way of grouping together a sequence of operations under a common name so it may be referred to multiple times, similar to mathematical functions, etc. We've already talked about the syntax of how a function is put together. If you have done the assignments by now, then you should be well familiar with how a function is constructed, because you've had to construct a few of them now. Right? Every single question that you had to do in your assignment required you to write a function, so you should be familiar with the syntax at this point. So here's some important nomenclature with respect to functions. In functions, you have the arguments or parameters that are specified in the function definition itself, and then you have the parameters that are given when you run the function. The parameters that are defined with the function are called the formal parameters, and the parameters that are given to the function upon execution are the actual parameters. So, formal parameters, actual parameters. The formal parameters are, of course, dealt with as you very similarly to how you would deal with variables in, normal execution. They're like variables that come predefined, if that makes sense. Even though, when if you're in a situation where you're the person designing the parameters for the function, you get to design what they are, so, they're still under your control to some degree. But, within the context of the actual statements, the actual code that's contained within the function, you can think of these as being, pre-established or predefined variables. Whereas, when we throw things into a function in order for that function to be executed, these might be variables, these might be literals, these might be any number of things. The whole idea is that they have some kind of concrete value, right? In the same way that a variable can't be written to before it's, or it can't be read from before it's written to, these actual parameters can't be provided unless they have some value to provide. And the reason, the way that this works underneath the hood in Python is that these are, the actual parameters are assigned to the formal parameters during the function call procedure. This is what's known as pass by assignment, which is that's the semantic structure that is used by Python in order to transmit data from the function call to the function's execution, right? That's what we call this. When a function is used, we call that a function call or a function invocation. Good. So, when a function is defined, the formal parameters are included in the function definition. When the function is invoked or called, the actual parameters are provided. During invocation, the function formal parameters are bound to the actual parameters. Python uses pass by assignment with each formal parameter assigned to the actual parameter. So, as I said, if you invoke change with T and C, T is assigned to target and C is assigned to coins. And when we say assignment, we mean assignment with all of the bells and whistles and trappings thereof. So if you remember from our previous topic 4 discussion, where we were talking about aliases, the aliases are established because when you perform assignment over a data structure, if it's a mutable data structure, you're not creating a duplicate of the data structure. What you're doing is you're assigning the memory address of that data structure to a new variable. And because both variables are fundamentally pointing to the same area in memory, modifying that memory through one variable changes that memory with respect to the other variable as well. So, yes, good. So this should be all mostly review. So here's a cool thing, though. Default parameters. Did you know when you define a function in Python, you may assign a default value to the arguments of the function? It is true. This is totally a thing that's possible. So, let me open up something here. Get it? Topic 5.py. There we go. So, let's say we define add 3, x, y, and z. Return x plus y plus z. Our simple function example. If we add 3, 1, 2, 3, print the result of that. Bum, bum, bum. There we go. Python 3. Oh, no. Python 3 topic 5.py. Bing, bang, boom. Our answer is 6, as one might expect. So, you can add default arguments. If you put an equal sign inside of the function definition line and give it some kind of literal value, has to be a literal value, so say z is equal to 0, you can actually omit that parameter when you call the function. If that parameter is omitted, you can see it'll use the default value. You can actually do this with all of the arguments of a function, and you can actually call that function with no arguments at all, and everything will still work. Cool. So let me just modify this function slightly so that we can see the difference here. I'll show you something cool. So by default, when you're providing parameters, any parameter that you provide, Python will assume it's being slotted into the first parameter slot, right? So if I provide a 5 here, it's going to assume that 5 is being mapped onto x, right? Because it's first. This is the first, that's the first, everybody's happy. So you can see it's being given to x, y and z are both having 0, which is as their default value. So our output for that particular instance is 5. Good. But what, my friends, what do we do if we want to assign, if we want to give 5 to y or z rather than x? How do we go about doing that? Well, it's actually relatively simple. You just perform a sort of mock assignment between the parameter that you would like this value to be attributed to, and that removes you from the requirement of depending on the positionality of the parameters in order to make sure that your assignments all line up correctly. So if you run this guy, you'll notice that we get 10 as the output because, of course, 5 is being given to y here, and y is being multiplied by 2, so 5 times 2 is 10. And, of course, if we wanted to do that with the final parameter z, we just assign z the value that we want z to have within the context of the function call itself, which means that we can actually, using this method, we can reorder the parameters of the function. We don't actually have to give the parameters in the order that they have been required to be up to this point. There you go. This might work without defaults. Maybe not. Let me see. Let me see if this works without defaults. Oop. Yep, so that method even works if you have no default methods at all. So this construction gives you a little bit more freedom. You no longer have to assume that, or you're no longer constricted to using the parameters of a function in the order given. So hopefully that's interesting to you. So, you know, just one final brief thing to dwell on here. When you have default values for parameters, if the parameter is given, if an actual parameter is provided for the parameter that has a default value, obviously the default value will not be used. Whenever an actual parameter is present, that actual parameter will be used. It's just, you know, you have the option of not using it if you don't want to. So there are a number of instances in Python where default parameters are used. It's one of the most common instances of it is actually in the print function, our old friend the print function. So you'll notice with print that we have a few of these default parameters that are included at the end that we can provide values for. So, for example, if we print hello world, normally with print, the parameter end is whatever character you want to end your whatever character you want or string you want to end what you're printing with, and separator is what the different strings would be separated by. Normally, the end is a new line, so every time you print something, it bumps the cursor to the next line for you. We can modify that. Baby. So if we say the end is changed to comma space baby exclamation mark, you can see that rather than including a new line character, it has put this string at the end of it, which is, what you might expect. Note also that this means that the cursor, the new command prompt, occurs on the same line as the things that we've printed, which is a little bit messy, which is probably the reason that there is a new line as the end character anyway. So yeah, that's all true. In general, addressing the parameters explicitly using this, explicit assignment is a good way of avoiding confusion with respect to, how many parameters am I using? Are these parameters, is it this one and this one? Is it this one and that one? The rules aren't that difficult, but it can be implicit. And, the drum I've been beating this whole time in class is when you have stuff that you can make explicit, you probably should, because that makes it easier to read and understand, not just for other people, but even for you yourself. So yeah, are there any questions about that? Yes. Lists as default parameters follow aliasing. So yeah. Cool. So, let's talk about scoping. So we've talked a little bit about this kind of idea. It's probably easiest to show in Python Tutor, I think. So let me just... Python Tutor. There we go. So, in order to understand what's going on with scoping, the sort of most correct understanding of it is to get into how the computer manages function calls themselves, which means we would need to talk about the stack, the system stack, and stack frames, and that sort of thing. But I guess within the context of this course, all of that stuff is considered to be kind of not necessary information for the level at which we're talking about programming here. I think it makes it easier if you understand what the stack is and what stack frames are. It makes it very easy to understand why local and global variables operate the way they do. So I'll give you as kind of the Coles Notes version of why all of this works, even though I don't have a slide on it specifically. So when you are running programs on your computer, the computer is constrained in that it can only really process one operation at a time. This is like the classical model of computing. Although there are, in recent years, we've seen the adoption of multi-core processors, which are capable, obviously, a CPU with 4 cores is able to compute 4 operations simultaneously. But if you actually get into how distributed computation works, it's actually a lot harder to split computing tasks over all of these different cores than you might think, unless you write code explicitly to use multiple cores. Like, for example, throw one function call onto a separate CPU core, for example. What often ends up happening is the computer will dedicate one CPU to executing or to running one program, and that leaves the remaining 3 CPUs to execute other programs, so the operating system can be running multiple programs in parallel. But, with respect to a single program being divided among multiple CPU cores, it's a more difficult task to program something to be able to do that, and so it's frankly just often not done, especially for, especially for programs that don't require that level of boosting with respect to runtime, right? It's not necessary to have solitaire taking up all of the CPUs in your computer. But, as things progress, we're beginning to get smarter about how we distribute computing tasks across multiple cores. But in general, the sort of classical idea of how computation works is still very much applicable, which is this idea that when you're executing a program, you are executing one operation at a time. So, have you ever wondered how the computer keeps track of which which commands it's executing at any particular time. Well, there's a thing called the system stack. When you execute a program, the correct way of thinking about this is that the computer steps into that program, right? It temporarily halts whatever it's doing and executes that program, right? So, again, this is a very sort of basic operating system type view of things, but it's roughly applicable. So let's say we have the Python process itself, right? So when I execute Python 3 and give it a file name, the computer has to load Python 3 before it can execute my script, right? So it loads Python 3. You can think of Python 3 as being the base layer of the program that I'm executing. On top of that, you then get your program with, well, let me rephrase that. With Python 3 sitting at the bottom, you then get your program stacked on top of that. That's why so it kind of runs like a stack of plates or a stack of pancakes. The idea is that you have a collection of program processes and sub-processes with all of their associated variables and memory and that sort of thing. If we use a plate metaphor, it's like your program has written on it like the variables that you're using. Like if each plate had a napkin on it and that napkin had written on it, the states of all the variables you were using, etc. When you run your program will invoke functions. When a function is invoked, a new plate is put on the stack of plates that has new variables on it, and when that function has finished its execution, whatever the return value is given to the plate below it, and the plate that function is removed from the stack. So it's kind of like in your kitchen, where you have a stack of plates in your cupboard. When you want to make yourself a ham sandwich, you don't take the plate that's on the bottom of the stack of plates. You don't take the plate that's in the middle of the stack of plates. You take the plate that's on that's on the top of the stack of plates, right? And then you make your sandwich on that plate. So it's like that. You sort of have a stack of plates, each one being a function, and then the computer will do everything it needs to do for that particular function, and then that plate is removed from the stack. So if you have this kind of model in your brain about how functions work, that's useful. And you can extend this idea for functions that call other functions. That is, you would have the Python plate, then you would have the first functions plate, then you would have the second functions plate on top of that. When you're finished executing function number 2, that plate is removed, and then the first plate is brought back up into focus, and then it's finished executing, and when it's finished, then you're back to your regular program. So, we can demonstrate this. We can demonstrate this using Python Tutor. Def F1 doesn't even matter. Return F2. Def F2, return cheese. F1. Maybe. Nah, that'll be fine. So let's just give some variables in here so that it looks like there's stuff going on. Nah. Stop that. There we go. Visualize. Invalid syntax. Gotta put a colon in there. There we go. So when we execute F1, notice we have a list of frames here. That's what the plates in the stack are called. They're called stack frames. So, and that's a pretty good analogy too, because if you imagine each one of these functions as being a picture, then, you know, the frame is the thing that contains the picture. So we open up a new frame for F1. It's highlighted, so this is the one that's currently being used, right? So we assign X. X is assigned within the frame, within the F1 frame, right? Now, in order to return a value, it has to calculate whatever the return value of F2 is. So we open up a new frame, put that one on top of F1. I know it's like reversed here. It's like on the bottom rather than on the top. But, you know, hopefully you guys have a sufficient degree. Hopefully you guys can perform those mental acrobatics to understand that it's the same thing but in reverse spatially. So we open up a new frame for F2. You know, we do whatever calculation is required by F2, and then it calculates the return value. The return value is then given to the previous stack frame. Since the, you know, that the return statement obviously terminates the function, you know, we then remove that plate from the stack. And then, you know, that's the termination of F1 here, so that's also removed. And since we're not printing this or anything, you know, we just return to the global frame and everything is hunky-dory. So this is an important thing to know, right? Let me just throw one more thing in here. So it's very, very important to understand variables as being tied to these stack frames, right? You'll notice in this particular example, X has been used no less than 3 times. Since, you know, one might ask the question, how on earth does the computer know which one of these 3 X's is the relevant one at any particular point in time? And the answer is, it knows because of the context in which, the context of the current execution. So, while the F2 plate is open, the variable X it's going to use is the one that's associated with the F2 stack frame, right? So, another way of saying this is the version of the variable that you're working with is always going to be the most local version that exists. So X is the most local version. We have a slightly less local version in the X associated with F1, and we have the least local or global version of X in the global frame. So Python is going to use whichever version of the variable is in the most local frame at any given time. So what that effectively means is that while you are inside of F2, it's the X that's defined within F2 that's going to be used, all other instances of x are going to be ignored, largely. And, you know, once we know the rules, we can start bending them, but this is roughly how it works. So the other important thing to note is that once F2 has finished executing, the x that was associated with F2 is actually straight up deleted. It is destroyed, it is annihilated, it no longer exists. The memory is deallocated. So the x that is associated with F2 does not outlive the execution of the function itself, right? Once the function terminates, all variables local to that function also are deleted. The memory is freed for other purposes. So, that's why that's why this thing works with, you know, if we have some q defined within the function, and then we try to print that q outside of the function, we get an error, name q is not defined, right? This q does not exist within the local frame, or within the global frame. We can, you know, we can get that to work reasonably easily if we just try something like this. So you'll notice there's no x in the global frame. It's all in the F1 and all in the function frames. When we attempt to print x2, there is no x that when we attempt to print x, there is no x that exists inside of the list of things that exists. So we get an error, name x is not defined. There you go. It's important to realize what exists and what doesn't exist. That's an interesting question. A function that makes functions. So, if you're interested in that kind of stuff, I would recommend taking the course 1JC3, which is functional programming. Within the context of Python programming, you're not going to see very much, not much of that type of manipulation. But that's because Python is primarily an imperative language. So Python is based primarily on the execution of these types of memory manipulation statements, you know, as we've been seeing in the course so far. In other programming languages, functions are first-class members, or, you know, that is to say, rather than modifying states in memory, most of what you do when you're programming in a language like Haskell is manipulation of functions. So, you know, where you know, this is something that you would rarely have call to do in Python, because it's just not how Python works. Having functions which make other functions is something that you do very commonly in Haskell. In fact, that's, you know, one of your primary methods by which you perform computation. So yeah, if you're interested in that kind of thing, I would recommend taking 1JC3. Although I'm sure anybody who's taken 1JC3 in the chat will say, take it at your peril, but so be it. So, oh my, God, I hate it when I do that. So, anyway, returning to the idea of scoping. So, in general, going back to here, stuff that's in the global frame is called a global variable. Stuff that's in any function frame is called a local variable and is considered to be local to the function call, right? So for this example, we can also think of things as being in scope past the point of their first assignment, right? So if you have a variable, if you have a variable x and you're trying to print it before it's been assigned to, that means it's, it doesn't exist yet. Even if you have x, an assignment to x after that, if you try to print x before it exists in the frame, you'll still get a name error, right? That's sort of in order to reinforce this idea that in an imperative language, the order of your statements really matters. The stuff that comes above, the stuff that comes before is actually executed before the stuff that comes afterwards. So, don't use stuff before it's been defined, basically. All of the code is at the top level of the program, or the global frame. Once this code is run, we can't call it again with different input. There is no reuse here, there is no modularity, all variables are global. This can be all that you need for certain instances, Very often when I'm doing file I.O., like writing a quick script to do some file I.O. stuff, it's often not worth the time to, write a function to do stuff. You just need it to do one thing, and you just do it. But in most instances, you want to take your code and you want to put it into function so that it can be rerun with different parameters. So again, if you have things that are defined inside of functions, those things only exist so long as the function exists. This includes parameters. So if we have a parameter y, or let's call it q, p and q, right? So we call f1, its parameter is p, and the value is 3, because that's the value that it's given, right? Notice that this is, again, operating inside of the local frame. This is not defined with reference to the global frame. So when f1 is no longer needed, p is deleted and is therefore no longer accessible. So, long way of saying that parameters do in fact behave like variables in this case. The definition of the factorial and print statements are top-level code, but the red lines are local to the function. These lines are local to the function. So yeah, functions enable modular design. We've been, talking about this a number of times already. So yeah, in this example, x and n are local to the factorial function, and these print statements will result in errors. I think I've already talked about most of this. Right. So the question then becomes, or let me just see if we have any questions. Is it possible to import functions from different files? Oh, yes. Oh, yes. Yeah, that absolutely. 100%. In fact, that's called an import statement. So, import topic 4. I don't think you need .py. Let me just open topic 4 to see what the function names are. Get it, topic 4.py. Make change? Yeah. So print make change. Actually, we can just probably copy this line. Oh, yeah, need to delete that, though. Is it make... I have to include that. There's definitely a way to do it. I'm just missing some syntax here. I'm sure Mark will step in there, or someone. Actually, that's kind of interesting that that's not Python import. Ah, okay. So, in order to access it, you have to do topic for dot make change. So, yeah, there we go. There we go. So, in order to use functions that, or anything really that you've defined in well, functions or classes that you've defined in another file, which incidentally, like, this is so useful that it's like you can't you would not attempt to do a, you know, even a medium-sized programming project without having this, without doing this. I don't know why it's not in the slides. You import the name of whatever file you want to use functions from without the file extension, and then you use that as a module name, use dot syntax to access the functions within that file. So, there you go. Yes! In the same way that you would use, like, the math library, you can use your own previous functions. So, there you go. Good. Let's see. It's 10:23. We should probably have our first break, yeah? Let's see, where are we? Cool. Yeah. So let's resume this class at 10:33. Okay, folks? Go grab a tea or something. Welcome back. We return. So, here we are. So, global variables then. It is possible. So, a thing that you can do if you want to access, for example, the variable q within one of the other frames. Actually, let's turn it back to x. That'll make it more straightforward. So we're sort of presented with a dilemma here, right? Which is, if we wanted to, for example, access this x in the global frame from inside of F2, we can't just call it x, because that, by default, creates a local version of x, which is distinct and different from the one that we are meaning to access, right? So, in order to actually access the x within the global frame, we're going to have to do something slightly different. This is not a thing that Python likes to admit exists, but we're going to have to use an explicit declaration. So the way you do it is you say global x. So if you declare with the global keyword that x is in this frame, but that the x that's in this frame is actually the x that's in the global frame, notice that instead of creating a new x that within the F1 frame, notice that this x is modified, right? That's because if you declare x as being a global variable, it'll be modified within the global frame, not the local frame. That being said, F2 still has its own instance of x. So this can be, this doesn't apply to everything, just the frame in which the declaration is made. So that's cool. But with respect to, like, the pardon me. With respect to the efficacy of that type of construction, generally speaking, it's discouraged. I'm kind of teaching you a little bit of black magic. I'm teaching you the dark arts. Not defense against the dark arts, just the dark arts. You've got there's a particular reason why it's sort of out of the way to, that using global variables in that way, you have to do stuff that's extra in order to do it. It doesn't do it by default, and there's a good reason for that. Over-reliance on global variables is the habit of bad programmers. It is poor programming practice in general to use global variables unless there's no other way of doing the thing you want to do than to use a global variable. And this is the reason. When you have a global variable, it's kind of like, for each global variable that you use inside of a function, it's kind of implicitly adding a parameter and an output to each function, right? Because a global variable can be like, the state of a global variable can have an effect on the execution of the function, it's an implicit input, right? And because any values that are stored in a global variable are, results that are being sent outside of the function, those are implicit outputs. So for every global variable that you add, you're increasing the complexity of the input and the output of that function, right? And again, that's not something that you want to do unless you absolutely have to. In general, a principle of good design is to minimize the interface, right? You want a function to function, so to speak, with as few inputs as possible. Only those inputs that are absolutely necessary to the function's processing should be included, and only those values which are absolutely required to be known by things that call the function should be the outputs, right? You want to kind of minimize the amount of bandwidth that are going into and coming out of any particular function. Again, the big old asterisk on the end of that is, without compromising the functionality of the program, right? It doesn't make any difference how, clean and well-formed your program is if it doesn't work or it doesn't do what it's supposed to do, obviously. But, it's sort of, like one of my favorite quotes, as a person who is an applied scientist rather than a theoretical scientist. One of my favorite quotes is by Eugene de Saint-Exupéry, who wrote The Little Prince, among other things. One of my favorite quotes by him, favorite quotes in general, that is by him, is, "A design is perfect not when there is nothing left to add, but when there is nothing left to take away." And that is true in so many instances, but especially in with respect to software design. Because in software design, you can very, very quickly and easily run into the overcomplexity problem. So keeping things simple is it's the best design advice that you can give someone. That quote is basically keep it simple, stupid, but in a more highly intellectual European style rather than in the American business sort of pragmatic style. But yeah, just whenever you're designing anything, keep that in mind. That the design is perfect not when there's nothing left to add, but when there's nothing left to take away. Minimize it. Make it compact. Make it, And this is actually, it's interesting because that even applies when you're, sorry, I'm going on a bit of a tangent here, but that even applies when you're doing something like writing an essay, or writing, even if you were writing fiction, like creative fiction, right? Include only those elements which further the goal of the piece that you're writing. Tighten it up. But anyway. So let's talk about software design. Actually, that wasn't a bad segue. So, in general, we have a couple of software design principles that we like to adhere to. These are the sort of basic level. I talk in these lectures about lots of different design principles, which are, I love talking about software design principles as principles for living your life as well. I feel that software design wisdom is wisdom that's generally applicable in people's lives as well as to software design. But, there are a lot more software design principles than just these, but this is as good a place as any to start. And we've already talked about this to some degree. So, modularity and decomposition. These are very, if you don't have decomposition down as a strategy for writing software, you will not be able to write software past a very basic level, right? So, what do we mean by modularity and decomposition? Well, it's all about problem analysis. If you have a problem, a very effective way to solve problems is to take a large problem, break it into a series of smaller problems, and then address those smaller problems at the level of the small problem, and then compose the solutions to all of the small problems into one big problem, or into the solution for into the solution for the big problem. And, again, this is very applicable to your life. Let's imagine that you're moving from one apartment to another, for example. Or even better, let's imagine that you're moving out of your parents' house, right? Moving out of your parents' house. Moving out of your parents' house is a problem, right? It is a problem because it requires effort and strategy. And if you don't, like, it matters whether or not you put in enough effort and have a good strategy, right? So, you know, in order to move out, you need a number of things. You can break that task down into a series of subtasks. You need to establish somewhere else to live. You need to find the money for first and last month's rent. You need to, you know, come to some idea of where you're going to get the money for rent for the place that you're going to live in. You're going to need to find all of the objects that you're going to take with you. You need to put all of those objects into boxes. You need to hire a van or something to put all of those boxes in to move to the new place. You need to you need to get that van to the new place. You need to unload that van with the boxes. You need to unpack those boxes, which are you need to unpack the boxes in order of essentiality, essentially. You know, that's a process that can take months, you know. But if you were to take a look at that problem and say, you know, I'm not going to break that problem down any further, I'm just going to move out, you know, I'm just going to decide one day I'm moving out, and then, you know, you just, you know, you can't do that without breaking the task down into subtasks, right? And the ability to do that is problem solving. Like, to a large degree, problem decomposition is problem solving, you know. There's a famous quote that might be misattributed to Einstein, that if I had 12 hours to save the world, I would spend 11.5 hours defining the problem, right? So that's the idea of modularity and decomposition. When you break a problem into subproblems, you want each one of those subproblems to be a task, right? A task is something that is a self-contained sequence of actions, right? Packing a box has a clear starting point, a clear ending point, right? You know when you're starting to pack a box. You know when you have finished packing a box, right? The procedure that you use for packing a box can be reused for many boxes. And, you know, there is a clear purpose to packing a box. It is to, you know, to make more easy the transportation of the objects that you put in the box, right? So this is the same attitude to which it's good to approach software with, right? I am going to write a function that does a particular task. I have a good knowledge of what the inputs to that function are. I know what the things, you know, in terms of boxes, I have an empty box and the junk to put in it, you know. The procedure of packing the box is what the body of the function would be, and a packed box is the output to the function, right? So you know what you want, you know what you have as the inputs, you know what you want as the output, and you have to come up with the procedure, right? But in software, it's like, it's not so intuitive what the inputs and the outputs are, because those are often going to be things that you are designing yourself, right? So yeah, modularity. The idea, modularity, modules, you want to be able to click things together. It's like Lego, right? The other way to think of software is like building Lego bricks, right? You want the functions to click together to construct a more cohesive whole, right? The manner in which functions click together like Lego bricks, basically the inputs and the outputs of functions are the knobs on the top and the sockets on the bottom of Lego pieces. You fit the inputs of one function to the outputs of another, you fit inputs to outputs, and eventually you've got a brick wall. So something that's modular is something that can be reused many times, right? Think about the space station, right? The International Space Station. The modules of the space station are designed with standardized interlocking mechanisms, right? So that if they ever want to just, if they ever want to expand the space station, all they have to do is send a new module up into space, and it already is built so that it'll click into an existing socket on the space station. So they just expand. They can expand the space station modularly over time. Modular design is extreme. Like, between modular design and reusable parts, that's the Industrial Revolution right there. So, or standardized parts, not reusable parts. Modularization and standardization are kind of very similar concepts. So, the other idea that we want to touch on is abstraction. So I've talked about abstraction a number of times. If you're looking for like a good general purpose definition of abstraction in the world, thinking about abstract art is perhaps not necessarily you want to go to that level of abstraction immediately. I prefer to think of it more like cartoons, right? Representational art rather than realistic art, right? So if you want to produce an image of a tree, right? You've got two methods of going about that. You can produce a realistic representation of the tree that includes as much detail about the tree as it is possible to include. One might take a photograph, for instance. Or, your other option is to produce a representation of the tree, which is recognizable as being a tree, but is not, like, the details have been left out, right? A cartoon drawing of a tree, for instance. And, there is, in the same way that the art of caricature, like, there is a very specific skill associated with drawing caricatures, right? In order to do a good representational piece of art, what you have to do is you have to isolate and emphasize the points of uniqueness about the thing you're representing, right? What is it that differentiates a tree from, a flower or a bush, right? The fact it's big, the fact it's got a trunk and branches, right? So, if you have a representational drawing of a tree, it's going to include a trunk and branches and leaves, generally speaking. Even though, the particular arrangement of branches, might be particular to a species of tree or whatever, but if you're just trying to represent trees in general, very quick, branch drawing inside of like a big thing that cloud-like thing that represents leaves, that'll get you most of the way there to this is a tree. And like the thing is, it's super, 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 super useful to be able to use abstraction to designate ideas, right? Using abstraction to designate ideas is kind of what human beings are all about. Like, this is, think about the symbols they use for different sports during the Olympics, right? It's like an abstract representation of a person like on skis or something, or doing in a bobsled or something, right? There is a real art to getting something as simple as it possibly can be while still representing the thing that it needs to represent. And so how does this relate to programming? Well, the function is the object. the interface of that function is the representation of that object. So if the function is the tree, the inputs and the output are the cartoon drawing of the tree, right? It's not necessary to know how many leaves there are on a tree to be able to, identify it as a tree. In the same way, it's not necessary to know what what all of the changes of state, what all of the if statements and loops are inside of a function. It's not necessary to know all of that stuff to use the function. And that's critical, because in software, in order to be a good programmer, you quickly learn that it's essential to rely on functions that either you have wrote or other people have wrote, right? So if the function does its job, you don't have to think about how it does its job. You just use it as a tool. You use it like a hammer or a wrench, You don't have to think about, oh, is this a solid core or a hollow handled hammer, or does it, is it made of carbon steel composite, or is it made of fiberglass? Or you don't have to worry about any of that. All you have to worry about is hammer hit nail, nail now hit by hammer. Good. 2 pieces wood fastened. You don't have to think at the level of that type of, in-depth analysis. And that's good, because, the more you can save yourself that kind of cognitive work, the faster you can work. And the faster you can work, the more likely you are to actually be able to program for a living. Trust me, as a person who has spent way too long doing his own thesis, because, to some degree, I was presented with a problem, which is, I was presented with a problem for my thesis, which these sorts of software, if I had adhered to software design principles more rigorously in the early stages of my writing my thesis, I probably wouldn't be in the position I am now, where it's like, I've been a PhD student for a very long time. So yeah. So let's talk a little bit about large programs. Large programs can be very large. When I talk about large programs, I generally like to bring in the analogy of video games, because video games are large programs. Like, a video game is very much a large program, right? It takes a hell of a lot of effort to develop even a very simple video game. And, if you wanted to develop something like, I'm just gonna choose Mario Odyssey because it's a cool game. That's gonna be my example. I don't know if you guys are like Rockstar Games people, or but I'm an old school Nintendo buff, so Nintendo is what I'm gonna be using. So take Mario Odyssey, right? That's the new Mario game. If you haven't played it, think, even aside from the visual assets, because most people, when they think complexity in video games, they think like, how complex does it look? But there is also programmatic or computational complexity behind these things as well, right? Like Mario's jumping physics, that's a whole physics engine, right? In Mario Odyssey, Mario has the ability to like take control of other characters in the game, and each new character that you take control of has like an entirely different set of physics that character operates by, right? And there's something like 50 different things that you can transform into, in that game, and each one of those has a different set of physics, right? So you can imagine if each set of physics is a set of functions that have been bundled together, and each individual thing that you can be in Mario is a different set of functions, that's already like a huge amount of complexity just there, right? So large programs have many, 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 many functions. Each function should be relatively small and be designed to do one thing only. So, going to the Mario example, each one of Mario's actions should ideally be one self-contained function. If you hit the A button, that calls the jump function. The jump function interacts with the, it sets up the preconditions in the physics engine such that, it initializes the, a jump arc, right? And of course, it's more complex because the longer you hold down the A button, the higher you jump. So there's complexity built into it as you're jumping, but, everything should do one thing, right? If you think, like, Mario's punch move that he has in Mario 64, that's one action, right? You hit the button, you get one action. Another example would be Twitter. So, Twitter is just a big database, right? That's all it is, right? It's a bunch of people who've said things. The things they've said are stored in a database, and you, in your Twitter feed, get a view of that database, right? You get a listing of the most recent entries in the database, and that's Twitter as an entity. That's all it is. So if you are tweeting a tweet, sending that tweet out, we think of it as like sending a tweet out, but what you should be thinking about it as is like storing it in the database, sending it to the database. So like tweeting a tweet, that is one function. Liking a tweet, that is a function. Deleting a tweet, that is a function. Attaching a picture to a tweet, that is a function, right? In a lot of these things, you can think of like each one of these options that you have in a menu, right? Each one of these options would be a function. Even if that function is bring up another menu, that's still a function, right? Cool. What is my thesis on? Ask me later. I'm teaching right now. I built a compiler for very obscure languages related to hardware design and verification of hardware designs. So given that we have all of these functions running around, it would be useful to be able to document them. So expecting someone to intuitively be able to know what the purpose of your function is unreasonable. It's unreasonable to expect people to read your code to learn how your code works. You should provide documentation. So when you write a function, let's use make change as an example here. In Python, if you include 3 quotation marks, that makes a quote-unquote doc string. The doc string stands for documentation string. This is automatically mapped to the output of the help function when it's called on your function. So if you provide a doc string for a function and somebody uses help to see what the help, to see what your function does, this is explicitly what's brought up. So there are a few things that you want to put inside of your documentation strings. Number 1, any assumptions, requirements, or preconditions. So what is the input that we're expecting here, right? You always have expectations for the input, right? Even if it's just in the form of, I expect an integer here. it's important for somebody using your function to know that a integer is expected and not a string or a null value or a boolean or whatever, right? So takes 2 arguments, denom and, or you can even do it like a list of things. Denom, a tuple containing denominations of coins in no particular order, and val, a target value computes a number of coins that add up to the target value, returns a dictionary mapping coin values to number of coins and there you go. So we've got a description of what the inputs are, right? Describing each of the inputs. We have a description of what it returns, citing specifically what type of data structure is returned, because, of course, you know, if you're actually going to use this function for some purpose, it makes a difference whether the thing is returning a dictionary or a tuple or a string or what have you. And then you have a description of the relationship between the inputs and the outputs. You'll notice, actually, that in many cases, this is how your assignment questions are formulated. In some sense, we are giving you the documentation for a function and expecting you to produce the function from the documentation. So, there you go. If we were to... let me just load up Python 3 there. Import topic 4. Oh, in the expected indentation. Okay. Will you like me now? Yeah, okay. So, topic 4 is imported. If I say help, topic 4 dot make change, look at that. There's the string that I just wrote. Ta-da! So you can see how that would be helpful. Incidentally, if you're not already using the help function to help you decide what the, you know, how to use the Python functions that you may wish to use, I highly, highly recommend coming to some degree of familiarity with the help function. It's extremely useful. So, there you go. Cool. Ugh. Right, let's see if we have any questions. My goodness. Yeah, I would be happy to discuss it during office hours. So, let's talk recursion. Recursion is a major topic in this course. You can expect a question on recursion to occur on both the midterm and the test. Or both the midterm and the exam, probably. So let's get into it. Remember our factorial example. This is how factorial has been designed, right? This is what you would call an inductive definition. N factorial has been defined in terms of n minus 1 factorial, right? So this is you can relate this to a style of argumentation, right? this line, if you took this line in the definition by itself, this would be a circular definition, right? For each time you try to define n factorial, you have to define n minus 1 factorial. So in defining n minus 1 factorial, you have to define n minus 2 factorial. In defining n minus 2 factorial, you have to define n minus 3 factorial, etc., 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 etc. You know, you go through all the numbers from the one you start on all the way down to negative infinity, which of course can't be computed because we can't compute infinities because we do not work on infinite computers. So this is kind of similar if we were to take the same style of argumentation in you know, human language, it would be something like, you know, what is a fish? A fish is a fish. Well, what is a fish? A fish is a fish. What is a fish? A fish is a fish, right? That's kind of, you know, that's the type of area that you're in, right? So the thing that makes this actually computable, the thing that makes this a recursive or inductive definition rather than a purely or merely circular definition, is the inclusion of what's called a base case. So the base case is one instance of the thing being defined without reference to itself, right? The factorial of n, the factorial of 0 is 0, or 1, sorry. The factorial of 0 is 1, right? It does not require any reference to any other definition of n factorial in order to compute. So the result of that is that if we, like, so long as the n that we start with is greater than 0, and is a, you know, a natural number, basically, as long as it's a whole integer, we will inevitably and eventually reach n is equal to 0, given enough repetitions of n minus 1, right? It doesn't matter how high n is, if you subtract 1 from it enough times, you will eventually reach 0, unless n is equal to infinity, of course. But again, we are not dealing with infinity, like, we are not dealing on infinite computers, so there's no purpose in, you know, that's sort of, when it comes to computer science, we can conveniently ignore the existence of infinity on the grounds that it cannot be computed by non-infinite computers. So, so we call these two instances the base case and the iterative or recursive case. The iterative or recursive case is the one that contains the self-referential call, right? Let me see how we're doing here. Good. So, I'm going to implement this in Python now. We are going to write a recursive function in Python. So, def factorial. And I know, like, we've done factorial before, but we did it with a iterative, a loop-based solution. This is going to be interesting because we'll be able to calculate factorial without using any loops. So the first thing that you want to do when writing a recursive function is you want to establish these cases, right? You want to differentiate these cases. So, if n is equal to 0, do something. Otherwise, else if n is less or greater than 0, do something else. So, we know that in the base case, if n is equal to 0, then the n factorial is equal to 1. So we just return 1. And in the case, the iterative case, we know that n factorial is equal to n multiplied by n minus 1 factorial. So, dun 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 dun, we return n multiplied by n factorial, or factorial called on n minus 1. This is the recursive call. The fact, so to speak, that the factorial function contains a call to the factorial function makes this a recursive function. So, let's just print here factorial of 6. Quit. Quit, I say. There we go. Python 3 topic 5.py topic 5.py. There we go. Just get rid of topic 4 there. Okay, so we get 720. Very good, we get the correct answer. So, the mental step that you have to make here in order to make this work in your brain, again, you can think of it in terms of stack frames. So let me load this up in Python Tutor, and we shall hopefully, this is not, hopefully Python Tutor doesn't crap out on this. Yeah, okay, cool. So we define factorial. We then open up an instance of factorial where n is equal to 6. In order to calculate that, so n is 6 is not equal to 0, so we go to the next case. N is greater than 0, so we go in here. In order to calculate the return value, we need to know factorial of n minus 1. So we open up a new stack frame for with n equal to 5, which is 6 minus 1. We go through the same process. We open up a new stack frame for n equals 4. We open up a new stack frame, new stack frame, new stack frame, and new stack frame. So you can see we've actually opened up 7 stack frames for this factorial function, each one with a successively smaller value. Now, we can calculate the return value of factorial. Its return value is 1. Now, the return value will be, now we can calculate the return value of the stack, the frame that was under that frame, and we can just follow the return values up through the various stack frames until the output is eventually produced. So that's what happens when a function calls itself. The function actually does call itself multiple times from itself. So it returns a return value from a previous, so it opens up a new instance of the function and it attempts to calculate it. If it needs to open up a new instance to calculate that, it will. It'll keep doing that until it hits, either the base case or the hypothetical limit for the number of recursive cases that you can have. So that's cool. So that's recursion. That's how recursion works. But you notice we were able to calculate this thing without using a single loop, which is cool. If you end up using the programming language Haskell. If you end up using Haskell, if you take 1JC3, in Haskell, recursion is used instead of loops. So Haskell actually it doesn't loop. I think you can get it to do loops, but it's not easy. It's like the native way in which Haskell iterates over data structures, for example, is by using recursion. So let me show you another example. Let's say we wanted to take the sum of a list, but we didn't want to use loops, right? Let's do recursive sum of a list L, right? So if the length of L is equal to 1, return L at 0. So in other words, the base case for this is that if the list only contains one thing, then the sum will be that whatever element is in that list, right? Otherwise, return L at 0 plus L, or the recursive sum of L at 1 to the end of the list. So what we're effectively doing here is we are taking the first element of the list, right? And we're adding it to the sum of the rest of the list, right? Unless there's only one thing in it, in which the sum is that. So you can see that in the same way that the factorial will continuously count down until we hit 0, in the same way, this recursive sum over a list will reduce the size of the list that it's calculating the sum over until it's just one element, and then it returns that element. So recursive sum of, let's just print the recursive sum of 1, 2, 3, 4, 5, 6, 5, 5, 6, 7, 8, 8, 8, 9, 10, 10. There we go. The sum is 85. This can be a bit more explicit if we, so print head is equal to L at 0, print tail is equal to L at 1 to the end. So you can see the head is at first 1, then 2, 3, 4, 5, you know, you can see that it's basically peeling off the first element of the list each time and reducing the size of the thing it has to calculate the rest over. So yeah, that's recursion. Notice we have calculated the sum of a list here without having to use any loops at all. So you can think of recursion as an alternative way, to using loops. So that's a good question. The question is, what is recursive? Is it a type of question? It's a type of solution. Within the context of this course, it's also a type of question. So, for example, on the midterm, if we are expecting a recursive solution to a problem, that will be stated explicitly in the question, and if you don't use a recursive solution, you're not going to get the marks, basically, right? Because we're trying to test you to see if you know recursion, obviously. However, if the question does not call for recursion, you're still permitted to use recursion on it. Recursion can be an extremely useful way of solving particular types of problems. If you can think recursively, that can make some types of problems much easier than if you did like a straightforward imperative solution. That being said, like, problems are not recursive or non-recursive. Solutions are recursive or non-recursive. So I would like you to associate, like, recursiveness as a property of a program, not a property of a question, right? Questions don't have properties, they have requirements, right? Test midterm question 3B requires a recursive solution. Therefore, the algorithm that you write must have the property of being recursive, right? Yeah. Problems are not recursive. Solutions are recursive. Cool. Yes. Precisely. Absolutely. It is a property of a solution which we can ask for if we want to see it. We can ask you to, write a solution that has that property. This is kind of one of the few exceptions in this course to this rule we generally have of you can find any way that you want to answer the problem by. When we ask for a specifically recursive solution, we expect a specifically a recursive solution. But yeah, anyway, we should probably have our second break. Let's resume class at 11:36. Until then, don't go nowhere. Don't touch that dial. Hello. Hello, 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 hello. I haven't had the picture freeze yet today. That's encouraging. I think switching the arrangement of chords actually worked. All right. Where were we? Ah, yes. Recursion. My favorite topic, because of the confusion that it elicits in all of the students who encounter it. So, this is, roughly speaking, this is the same as the version of it that we came up with in the slides. So, you'll notice this is kind of the way I go through the slides, is like, I do what the slides might say, and then I check to see if I got it right, and then if I did, then it's like, okay, you know, so it goes. So, here's an interesting thing, though. We kind of already did this when we displayed the stack frames in Python Tutor, but you can also get to the same place by using print statements. So if we print at the beginning, fact called with n equals, and then the value of n, print returning 1, print, sure, that's fine, leave it like that. And then if we execute that, we'll be able to see somewhat more explicitly in terms of like procedural elements. You know, fact called with n equals 6, 5, 4, 3, 2, 1, and 0, returning 1, and I suppose we should put something in here. Something like x is equal to fact n minus 1, or n times n minus 1, return x, print returning then x. Then you can see the return values that are being printed. We're sort of accumulating the x, or the return value, in the same way that we would return it if we were using a loop. Like we're accumulating it as if it were a loop. So what's happening is that the accumulator variable that we would be using inside of the loop, if we were doing this with a loop, is implicitly the return, the sequence of return statements. You know, it's like, yeah. If you were to expand out the definition, that's another way of thinking about it. So, factorial of 3 is equal to factorial, it's equal to 2, or 3 times factorial of 2, right? Which is equal to 3 times 2 times factorial of 1, etc., etc. That's, you know, it's sort of implicitly all bundled up in one expression, right? But, yeah, anyway. So, yes. As we demonstrated in Python Tutor, every time we recurse, so recurse is like the verb, and recursive is the adjective. That which recurses is recursive. Every time we perform a recursion, every time we recurse, the interpreter creates a new scope for the variables in the function. as demonstrated, in Python Tutor. Python Tutor, there we go. So you can imagine, if we were to edit this code, if we had some variable in here that's not important, in the same way that in the same way that we were, having variables in there when we were dealing with scoping rules, when we create a variable inside of a recursive function, we have a copy of that variable in each of the sort of most local versions of that function call, right? All the way on down. So that's another thing to keep in mind, is that scoping rules apply to recursive calls. So, again, sort of in the same way that you would use a regular function, if you want x to refer to something outside of the current frame of the recursive call, you're going to have to make that guy global. Yes. So, recursion. So why would we use recursion? Why on earth would anybody use this method to solve anything when loops exist, right? Well, it turns out that recursion is actually a natural problem-solving technique for problems that have a, quote, inductive structure. This is not going to be so much a thing presently, right? To put it one way, until you start working with more advanced data structures, you're not going to see many applications where recursion is going to be the quote-unquote natural technique. However, once you start getting into advanced data structures, if you decide to take more computer science courses after this, if I haven't completely scared you off, data structures that have a sort of inductive structure are highly amenable to recursion. Data structures such as trees, for instance. A tree is, well, I'm not sure I can really get into what a tree is, but maybe I can show you a picture of one. Binary tree. So this is a binary tree, right? With this is a data structure that has an inductive structure. Each node has at most 2 branches, and each branch points to another node that has at most 2 branches, right? So if you had a data structure like this, and you wanted to write an algorithm that would, for example, find the maximum element inside of this tree, it would be you would prefer to write a recursive algorithm. So the recursive algorithm would look something like, compare the node and the maximum of this node and take the maximum, right? And to know the maximum of this node, you take this node and the maximum of this branch and that branch. And in order to know the maximum of this branch, you need to take that branch and that branch. So it's sort of, the recursion would naturally follow these arrows within the graph, within the tree structure itself. It would be a natural way to solve a problem over this type of data structure. This type of data structure is not the sort of thing that we're going to be dealing with a whole lot in this course. We do have a tutorial that we talk about. We touch on this. On these guys. This is like, from the perspective of 1MD3, this is like an advanced topic at best. So just keep in mind that if you are going on in computer science research or computer science courses, and you end up taking like a data structure and algorithms course, this is by far, like, these types of structures are by far the shallow end of the pool when it comes to data structures. So, you know, recursion is a very useful thing. It's you know, like anything in programming, it's situationally dependent, right? But yeah, depending. So you know, think of recursion as being a tool. Like any tool, there are some situations that it's great in, and other situations that it's terrible in. We're gonna show you one of the situations it's terrible in right now, actually. But let me see if there are any questions first. Nope. Cool. So, a well-known sequence of numbers that probably most of you are familiar with is the Fibonacci sequence. The Fibonacci sequence is another it's another example of a thing that has an inductive structure, right? That's because each new element in the Fibonacci sequence is defined with reference to the two previous elements in the Fibonacci sequence, right? That's what defines it. You start with 1 and 1, and then from that point on, every other element is the sum of the two previous, right? And that's what this mathematical case expresses, right? If you're talking about the 0th or 1st element of the Fibonacci sequence, those are both equal to 1. However, for all elements greater than that, it's the sum of the preceding two. Cool. So let's write an algorithm. Algorithm. So, define fib n. If n is equal to 0 or n is equal to 1, return 1. That's the base case, right? Very straightforward. Elif n is greater than 1, return fib n minus 1 plus fib n minus 2. So, let's compute the 5th Fibonacci number and print it. Yeah, blockhead. So the 5th Fibonacci number is 8, right? Of course it is. If you start counting from 0 anyway, it goes 1, 1, 2, 3, 5, 8. So if you start counting at 0, then the 5th Fibonacci number is 8. Fine, cool. All right. So what if we want the 10th Fibonacci number? That's 89. What if we want the 15th Fibonacci number? Cool. What if we want the 20th? Cool. What if we want the 30th? Oh-ho. Did you see how long that took? 31st. 32nd. Now here's a little Linux trick for you. If you run a command with the time key, command before it, it'll run the command and then it'll tell you how long it takes that command to execute. So in this case, in order to calculate fib32, it takes us 1.3 seconds. How about fib33? 2.2 seconds. Fib34. 3.4 seconds. You can see that as we're increasing the number that we're trying to execute, or that we're trying to calculate, we're running into longer and longer and longer run times. You know, normally I say stuff like you know, optimization doesn't super matter at this level because it's unlikely for you to be able to write a program that won't run in a fraction of a second anyway for the size of the problems that we're working on, right? Well, we've hit one of these cases where this solution to the problem is so inefficient that we can't even calculate things like, you know, fib 100 would be completely impossible for us to calculate. It would take weeks. Literally weeks. So, that's because what's going on here is actually the amount of runtime is it's sort of proportional to doubling each time. So, you know, if we tried something simple like 38, you know, doop-a-doop-a-doop-a-doop-a-doop-boom, how long's gonna take? It gonna take lots of time. Lots of time. I interrupted it at 15 seconds because I decided that was too long. So, you know, you see what I mean? We gotta come up with a better solution. There's got to be a better way. There will be. But this is what you would call your naive implementation. So, when you talk about, like, optimized solutions, it's like useful to know what the opposite of an optimized solution is, what the nomenclature for that is. Normally, we call the opposite of an optimized solution either a naive implementation or a brute force implementation. Naive because it's, you know, the optimized solutions are often more complex. They require more cognitive, you know, development, like, it requires more brain to do an optimized solution than a non-optimized solution. So we call them naive sometimes. The other moniker that they get often is brute force solution. So rather than optimize the algorithm, we are relying on the raw processing power of the computer itself to calculate the whatever it is we want to calculate in whatever time we want to calculate it in. So rather than having an efficient solution, we are relying on horsepower, so to speak. Boop. Let me see what the chat's doing. So we're going to make this more efficient without using loops. We're going to continue to use a recursive definition. But first, before we know how to make it more efficient, we have to have some idea of what the problem is, right? So, let's take a look. Let's take a look in Python Tutor. Actually, that would be useful. So, Python Tutor, there we go. Edit that code, doot-de-doot, there we go. So rather than do 32, let's do something simple like 5. Visualize. So, we're going through our code, right? We open up an instance of fib with n equals 5. In order to calculate that, we need to know fib at n minus 1, so we open up 1 for 4. We need to know, so it calculates it n at 4. So then it needs 3, then it needs 2, then it needs 1, then it returns 1. So then it needs 0, right? So so 2 needs 1 and 0, so it calculates 1, then it calculates 0. Oh my goodness. Oh, that was terrible, I apologize. There we go, calculate 0. Then we can calculate the return value of n equals 2, which is 2, right? That's used by n equals 3, but then it needs to calculate n equals 1. So that's return value of 1. So once it calculates n3, fib 3, it has to calculate, fib 4 has to then calculate fib 2, right? So you see the problem here. The problem is that in order to calculate any of these, kind of similar to the trees that I was showing you, calculating any particular Fibonacci number sort of generates a large number of recursive calls to Fibonacci. In the case of factorial, factorial was relatively simple because it only required one recursive call each time, right? The iterative, or the recursive case, or the iterative case, contained only one call to factorial to calculate factorial. In Fibonacci, we require two calls to Fibonacci for every call to Fibonacci. That means for every number you go up, you're getting approximately 2 to the power of n calls to Fibonacci. So, that blows up pretty quickly. That, 2 to the n goes, 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, etc., etc. Like, it doubles for each layer of recursion that you throw on top of it, right? And I've got a picture of that. Yeah, so if we were to calculate fib4, fib4 requires fib3 and fib2. Fib3 requires fib2 and fib1. Fib2 requires fib1 and fib0. That gets calculated. We then head up that. So, and you can, if we calculate fib5, fib5 requires fib4 and fib3. So you need a duplication of this tree and a duplication of that tree. So, that adds complexity very quickly, we don't really start seeing how terrible this solution is until we hit the computational limits of the system we're using. In my particular case, this, I don't even know how old this laptop I'm using. I think it's like 5 or 6 years old, this laptop that I'm using to do all of this with. It calculates up to about, 35, and then it starts running into, or 32, and we're starting to hit noticeably long run times, right? That's a pretty low cap, actually. So, okay, so what do we do? What do we do about this, if you include a counter variable to count how many times Fibonacci has been called, that's, that might also be useful, actually. Let's do that in Python Tutor. So, count, call it C equals 0. Global C plus equals 1. So, every time we execute that now, we have a C variable in the global frame that keeps track of the number of times the Fibonacci number, or the Fibonacci function has been called, right? So, by the time we get to the end of it, we've called Fibonacci 15 times. If we increase this to 10, by the time we're done with all of this nonsense, we've called Fibonacci 177 times, right? You can see that this is quite a steep rate of increase. And that's the problem, right? But yeah, we can define, we can sort of, in terms of, like, you remember back in the first set of lecture slides, I was saying how you can characterize an algorithm by properties of the code itself, but also by the amount of time it takes to execute. Well, you've seen both of those now. We measured the terribleness of Fibonacci, the naive Fibonacci implementation, using, actually timed executions on my system, and we have seen Fibonacci, the sort of theoretic although I guess this would also be empirical because it's the number that is derived from running it, but, the number of times the function is actually invoked is also useful, right? Information. So we're going to use a more advanced technique called dynamic programming. Let me see what the chat's saying. Yeah, so Adam has come up with the solution. The manner in which you can optimize this algorithm to make it run less terribly is to make the simple observation, hey, there's a hell of a lot of repetition going on here, you know? Do I need to run do I need to run this function twice in two different places, you know? Or, you know, you can imagine if you had fib 20, you only need to calculate fib 19 or fib 15 once, right? If you save the value that it produces. And that's the thing. That's the thing. Essentially, what we're doing is we're trading off function calls for memory by storing the intermediate results that are produced when the function is called. So essentially, if rather than just going for it with these calls to Fibonacci, if we keep a data structure that contains intermediate values and we check to see if those values are in the data structure first, then we can skip some recursive calls to Fibonacci. It turns out we can actually skip most recursive calls to Fibonacci. Overwhelmingly most of them. The overwhelming majority of the recursive calls going on here are completely redundant. You know, if I modify this guy to also keep track, you can see that for fib 32, the number of times that the Fibonacci function was called was, 7 million times. The hypothetical limit to the number of times you would have to to the number of times you would have to execute Fibonacci is actually the number that is indicated, right? Plus 1 for the 0. So to calculate fib 32, if we're storing our intermediate results, we, in theory, only need to calculate fib 33 times. So, what percentage of 7 million is 33? It's a pretty low one, right? And this becomes even more and more and more efficient the more you run it out for, right? So, yeah. So let's do an implementation of that. So first of all, I'm going to make a, this is called memoization. I'm going to make a memo variable, initialize it. I'm going to make the default an empty dictionary. And I'm going to say, rather than just returning result, rather than just straight invoking this, I'm going to create some variables f1 and f2. If n-1 is in the memo, f1 is equal to yeah, I'll do this and then I'll optimize it. f1 is equal to memo at n-1. Else f1 is equal to, or sorry, memo is equal, or memo at n-1 is equal to fib n-1. And then f1 is equal to memo at n-1. Right? That makes sense. That makes intuitive sense. Hopefully. So we're checking to see if the integer n-1 is in the memo. If it is, then we assign it to this intermediate variable f1, which is then going to be used to return the result. If it isn't, then we add it to this first. Now, we can perform a few logical optimizations on this to kind of, make it take up less space. Let's do that now. If you have a statement at the end of all branches of an if statement, it doesn't need to be in the if statement. It can be after the if statement, right? There's no difference. So we can just do that. If there's nothing in the if branch and something in the else branch, then what you want to do is you just want to say not, right? You just want to perform the Boolean inversion there. So if n-1 is not in the memo, add it to the memo, and in all cases, f1 is equal to the value that's in the memo, right? We have to add it to the memo before it's being drawn from the memo, because, you know, it's the you can't read from a variable until you've written to it problem. So if n-2 not in memo, memo at n-2 is equal to fib n-2, and then f2 is equal to memo n-2. And in fact, you know, if you want to get right down technical and optimize this even further, you don't really need these intermediate variables either. You can just sort of directly, since they're not being modified or anything after their initial assignment, you can just sort of substitute them directly into the expression, and then you can save yourself some memory. So there you go. One thing, though, what did I forget? I forgot to pass the memo back into the recursive call, right? It's like this is now an argument. If you leave it blank, then it'll start off blank, but in all subsequent executions, all recursive executions, you should really be passing the memo down. Now, it turns out that it actually works if you don't, but, you know, it works if you don't for aliasing reasons, and we'd prefer an explicit solution to an implicit one, right? So, let's do the same thing. Ha-ha! So we come to the same answer, but rather than having 7,047,155 calls to Fibonacci, we now have the predicted vet number of 33. Bing, bang, boom. So, so there you go. This is a much, much, much more efficient solution. But let's pop it into Python Tutor and see what's actually going on here. So, you can see, well, 33 might be overdoing it, actually. Let's just do it for 10. That'll probably be enough. So, we invoke the fib memo, right? Memo is an empty dictionary. We then make a recursive call, right? Because in order to add n-1 to the dictionary, we have to make a recursive call. So we are making recursive calls all the way down, all the way down. Down, 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 down. I want to hit the point where it's... So, when we hit n equals 1, we get a return value of 1. So, once we do that, we now have a dictionary where 1 points to 1. We then can, then from the fib2 calculation, we'll also need fib0. Fib0, it gets calculated and also added to the dictionary. Ta-da! So, we now can calculate the return value for n equals 2. And when we do, that gets added to the dictionary. And then, as we go through, each one of these fib instances gets added to this running dictionary of all of the values. And rather than having to step into recursive calls to, you know, for example, 8 requires 7 and 6, right? Once 7 has been calculated, it had to calculate fib 6 in order to get fib 7. So, since fib 6 is an intermediate result, and we're keeping those intermediate results now, fib 8 can look at the result that was calculated during the calculation of fib7 and use it. And that's what it does, and that's how it gets its return value so quickly. Blammo! So that's how it works. Memoization. Ta-da! Let me see if there's any questions. Yeah, so it's all as Mark points out in the chat. This is something that you have to implement in Python. You should get used to the idea that a computer is not going to perform a huge amount of optimization for you, especially when it comes to this type of quasi-data structure stuff. A certain amount of memory management will be optimized for you, right? Even in C, a certain amount of memory management is optimized for you. But when it comes to like algorithmic design type areas, very rare is it for a computer to take a recursive function like this and to memoize it for you. Haskell might do a certain amount of that. Haskell has a reputation for being a very well-optimized programming language, but certainly in imperative languages, what you see is what you get with respect to the algorithm that you write down. So, yeah, I kind of jumped over a couple of topics to get to fit this, to get into memoization, but we'll just cover this quickly. So I showed you some, I showed you some runtimes for Fibonacci. Here are some other runtimes in terms of seconds. So you can see, you know, when you start getting into like numbers like 40, you're starting to run into like a minute and a half, which is just ridiculous. Runtime scales exponentially with n, which means it's like adding 1 to go from 40 to 41 takes like almost all of the amount of time it took to go from 0 to 38 or something. Memoization. So the idea for memoization is that we save intermediate results and use them to avoid unnecessary recursions, which is good. So this is, roughly speaking, what we did. Actually, that's exactly what we did. So I guess the one thing that we didn't do is to test to see how far up we can go now with these guys. So let's just do something ridiculous like 32, 320, or 3,200,000. Maximum recursion depth exceeded. So that's a different problem, right? So Python will prevent you from recursing any further than 5,000. So I think you can do 4,999,7, something like that. Nope, still okay. Might be 1,000. Yeah. 998. Yeah, there we go. So the 998th Fibonacci number is this, which is large. So you can imagine if we had to run twice that number of recursive calls in order to calculate that number, how long it would take us. A long time. So yeah. So our runtimes are like so much less now. In fact, our runtime now scales linearly with n rather than exponentially on n. So another way of saying that is that for each additional value, or for every 1 that this number goes up, you're adding approximately the same amount of runtime each time, whereas previously you were doubling the amount of runtime each time, approximately. So that's, you know, a much more efficient solution. So let me just go back and cover a couple of things. So in this example, we were using a couple of different methods of measuring the efficiency of the algorithm, right? So runtime is a big one. Runtime complexity. What is the approximate number of basic operations the algorithm will perform for a certain set of inputs? So that's like measuring how many, that's direct measurement of the source code itself. That's the theoretical approach, right? How many times is X statement going to execute? In terms of practicality, or pragmatically, or empirically, you actually try to run it and see how many seconds it takes. You can do the same thing with memory, actually. So the approximate number of variables that the algorithm creates, right? You can measure that by reading the source code. You can also measure that empirically by seeing how much RAM does the implementation take, which I believe is in Linux htop. Yeah. So so in your computer, right, you have a certain amount of memory, right? And if you have sufficiently sophisticated mechanisms for you know, for displaying this information, you can see how much memory each of your processes take. The equivalent in Windows of this is the Control-Shift-Escape task manager. You can see how much memory each process is taking. So you can measure that kind of thing about a program as it's executing, right? So, yeah. And also, just so you know, this will be our last thing for today. It is possible to get into infinite recursion the same way that you get into an infinite loop. So a good example of that is if we take a look at our factorial example, we've got factorial doing specific things for n being equal to 0 and n being greater than 0. But if rather than, what if we just made this an else case rather than for n greater than 0? Let me just Python 3 topic 5.py. There we go. So if we call it with 6, everything works, right? But what happens if we call it with, for example, -2? What happens is we never actually hit the base case, right? The base case is 0. If we start off with a negative number and subtract 1 each time, we never hit 0 because we're moving away from 0, right? We're moving away from 0 towards negative infinity. So we never actually, like, we'll never hit the base case, and because we never hit the base case, we never hit an instance where a non-recursive solution is presented to the recursive problem. So this becomes an actually circular argument, right? And eventually you'll just hit the recursive limit of Python and everything shuts down. Which, by the way, is 1,000, not 5,000. So how do you protect against that, right? Well, we had it right the first time. If you simply exclude from consideration cases that will lead to unstable behavior, what you get as a result is actually a none value. It should be anyway. What's going on here? Oh, less than. I meant greater than. There we go. So, if if the particular value of n is like outside of any if statement that's being considered, you'll end up with a none, which is what Python returns if it ends a function without hitting a return statement. The other thing that you can do is you can have an explicit return statement. You can say return false, or, you know, we're going to see this in a little bit, raise value error, which creates an error. So you can do something else for inputs that are outside of the domain of the recursion, right? The other thing that, you know, might happen is, for example, with our Fibonacci number, if we accidentally, you know, put a 3 here instead of a 2, then, you know, we would at some point skip over fib 0 and 1 and go to fib -1, and then we would have the same problem as we have with factorial, right? So yeah, so that's recursion. If there are any questions about that, please put it in the chat now. Otherwise, I will let you guys get to your tutorials. Yeah. Well, one thing that you have to be careful about with respect to, you know, judging how many people are actually watching these things is that a lot of people are, like, probably a majority of people are watching these things after the fact, engaging with the material asynchronously, which I understand. It's a summer course, right? So people have, like, jobs and stuff. So I don't care if you watch it synchronously, but you should watch the lectures, for sure. Of course, I'm preaching to the choir right now, but yeah. When are my office hours? Thursday, 10:30. Thursdays at 10:30. to 11:30. I actually forgot my office hours last week. Sorry, guys. I'll do it this time. I'll be there this time. Terrible. I'm a terrible person. All right. Well, if there's nothing more important or pertinent for you guys at this particular point in time, then I'll sign off here. Good luck with the tutorials and everything. We'll get everything together. Once again, the secret to understanding programming is practice. So you gotta practice. Practice, practice, practice. Practice makes perfect. Take her easy, folks.